Okay, so let's get started. Last time we were talking about the Risc-V Isa and how to write the assembly code for Risc-V. And no matter if you have learned Risc-V or other type of instruction set before or any assembly language, it looks pretty much the same for all the languages. Like it may have different name for different instructions, but the principles are similar. So I assume you can, like at this point, you know how this program is constructed. That there may be some program that is very hard to write for you manually, but at least if I give you enough time, you should be able to write a program in assembly format, right? So starting from this point, let's work on the binary format. So how these instructions are encoded in Risc-V format. I'm not going to cover all the details about the binary format. It's rather boring. So eventually you still need to reference to the official document to understand what's the binary encoding. But I will just try to cover the most useful part. So Risc-V uses several different types of the instructions, because for each instruction, you only have 4 bytes to encode the data, to encode the instruction. For some instruction, you have immediate values. For some other instruction, you don't have immediate values. So to be able to support all these instructions in only 4 byte size, you have to reuse this size. Then if you learn the old school C style, this is typically represented in a union data structure. But in more advanced language, we do not use union anyway. When we decode, we just simply have multiple, like different fields there, like duplicated fields there. So, like for example, I know in our disassembler assignment that eventually you're going to write a disassembler for Risc-V. For example, in R type, we have RS1, we have RS2, right? Then there's only RS1, RS2, but for I type, there's no RS2. So you can just keep RS2 there, then just don't use it in case it's I type, okay? Just have all the possible fields, then to have a struct that named as instruction, then you can decode. Decode is the process that converts from the binary into the instructions. Then you can also print. Then print means you print from the instruction to the decoded instruction, a struct, into a string, so that you know, okay, we printed this line, it's exactly the same as the original instructions. So looking at the assignment forward, I think eventually you're going to work on a disassemble assignment. After the disassemble assignment, you will be working on emulation assignment. So basically, if I give you a binary format of the code, you first need to disassemble the instructions. Then the instructions will be fed into an emulator. The emulator will mimic the behavior of a Risc-V core and generate the result. Okay, so then you need to understand this binary format so that you can decode it and use this information to recreate the behavior of a Risc-V core. So there are 6 different types, or four categories of types, right? For R type is mainly for registers, and I type is for immediate values. S type is for it was S. B is for branch. B is for conditional branch. J is for jump. Let's look at the examples. I don't exactly remember what it is, the S type. What's the S instructions? Like, I think we have S instructions before. So let's look at the examples, how this encoding is done. So this encoding is all done in this way, right? So like certain bits represent different things, right? So this op is 0 to 6, is the lowest bit in this 32-bit range. So you need to take 4 byte number and rearrange it as 32 byte as a 32 as a 32-bit number, right? uint32. Then you need to start to extract useful bits from the binary. And let's look at what's the R type. R type has op as 7 bits, which this is a typically in other languages it's called opcode, but sometimes you can also combine func3 and func7 as part of the opcode. So this op is basically encoding tells what instruction it is. For example, for both add and subtract, then the opcode is 51. This is just by definition that they define 51 is add. So why they use this number? It's actually because in this opcode, this op field is not only encoding 51, this single number, they're encoding some extra information. For example, I know in Risc-V, they have this rule that if it starts with 1, we know this instruction is only 4 bytes long. Now, if it starts with a certain sequence at the beginning, it can be more than 4 bytes long. Okay, so the first few bit determines if it's a like 4-byte instruction, 8-byte instruction, 12-byte instruction, or even more. Okay, so these are the encoding value. That's why they select these trivial instructions, but they select not that small number. So because they're internally encoding some information. Then we look at op. We also need to look at func3 and func7. So we see all of them are 0, right? Are they 0? Oh, this one is 32, right? This one has a 1 there. This has a 32. So then once we look at these 3 fields, we know we can identify what instruction it is. Then we need to perform a table lookup. We need to look up in the table. So this is the Risc-V table that I take a screenshot from the official document. Then this is the RV32I base instruction set. And you can see those are the whole instruction set. And there are only these instructions, right? There are only not many. I don't know how many of them, but probably less than 30 of the instructions here. So these are all the instructions. Then we'll first look at op, right? So you can see the ops are not very different. There are only a few options. 1 1 1 0 0 0 0. This one 1 1 0 0 0 1 0. Then 1 1 0 0 1 1 0. Not many options here. So in this case, we first need to identify what op it is. So we're looking for this op that is 1 1 0 0 1 1 0, right? So then look at this table. We need to look to find it. You can find where it is here, right? You can find it here. So you know it's either add, sub, shift left, shift right. Is shift right here? Shift right? No, it's shift right is not here. Shift left, add, sub, SL, L, SLT. Those are the instructions here. So then we need to look at this func3 field and func7 field, right? So look at func3 field. We see this one is 0 0 0. Then this one is 0, all 0, and there's a 1. Then we know, okay, this one is a sub, this one is an add, if 0 is an add. Just by checking these 3 fields, we know what instruction it is, right? That is our op, the mnemonic, that we can identify the mnemonic. In other language, I would call the whole thing as an opcode. But in Risc-V, they define something as op, func3, func7. I think Risc-V is really trying to make it really tight. Their encoding is really tight, so they have done something really not that decoder friendly. Okay, but it's okay. Then, by looking at these instructions, we immediately know these are the add and sub instructions, right? Then we need to look at what is RD, what is RS1, and RS2. We know those are 5-bit numbers. So when we have 5 bits, how many registers we can encode? We can encode 32, right? So at maximum is 32. Then remember last time we were talking about the registers, and they have 2 different names. One is a more architecture name that is always X something, which is the other one is more assembly name, which is S, T, or there's other names. You have the other table that you can look up for if that's a number, that's something of the register name, right? And you can convert from a few digits into string, right? By doing several layers of table lookup. So this is the R type. The R type is probably the most straightforward type. And probably the only challenge that eventually you will encounter is how to grab the right number of bit out of this instruction. But I think after a few try with a few like shift operations, with a few like bytewise and bytewise or, I'm pretty much sure you can extract the right bit out of the instruction. Okay, so this is R type. Then let's move on to see other types, I types. I type stands for immediate, so the big part is occupied by 12-bit immediate number. Then, so in this immediate number, you actually need to slightly look at what's the immediate number represents. For most of the time, the immediate number is just two's complement encoding. So we can write in negative number, we can write in positive number, or we can write in hex number. Then the decoder can process it. So there's a question that if you are printing, you're disassembling, you're printing the instruction, in what format you need to print, then I have no certain answer. So the solution you need to do is to check the official disassembler. You don't need to check the original code, but just use the official disassembler to disassemble this file. Just keep consistent with the official disassembler. The only purpose of disassembling the code in a simulator is to make sure that we understand things correctly, right? So if we can print exactly the same thing, no matter if you print it in the hex format or in a negative number, it's okay. Yeah, and then this one, like for something like this one, shift right arithmetic I. So we define that only certain range of bit matters. There's a range. So for example, if we shift right, there's no point of shifting more than 32 bit, 32 times, right? So that means the upper bit, only the lower bit matters. The upper bit, we ignore that part. Okay, then we have S type. Oh, S is for store. Now finally remember, S type and B type. B is for branch. Now, as for store, then it is developed in this way. So it actually requires two registers, but both of them are source registers, right? So we're storing a value. One is storing, say in this case, T2 is storing the data. S3 is storing the address. Okay, so there's a definition, say which one is which one. I still need to look up to know which one is which one is the data, which one is the address. You cannot invert it. Then other than these two source registers, we actually need an immediate number to give it an offset. That although it's written, the address is this way, and we're doing something like S3 minus 6, right? Minus 6, then that's the actual address we're using. In this case, this minus 6 is stored in here, in this immediate part and in this immediate part. And how it works is you need to take these two immediate part out, then combine them together. Then that's the number that you are eventually looking for. Okay? So combine these two together, then make a number. So why they are designing in this way is mainly to keep it as consistent as possible. See, if we're talking about RS2, they're all at the same location. RS1, they're all at the same location. For RD, we don't use RD, right? If we don't use RD, we can use this space for immediate. So they want to keep a little more consistent encoding. So I would say some ISA is designed in this way. Some ISA is designed in a way that is they don't consider this alignment. They consider like, oh, I wanted to, for easy decoding, then they put all immediate to the end. Then even if we have different format, we don't have the destination register, then we just do something like, if it's different type, just arrange it from the beginning to the end. So different ISAs define things in different ways. Okay, then also we have this is S type. Yeah, it's all the same thing. Then we also have a B type. B type is for branching, conditional branching. Then conditional branching is even more annoying. Now, I don't know if you understand this part. It took me a really long time to understand what exactly is going on. So what's going on is this bit is for the most significant bit of that immediate number. Then we need to take this bit as 11th bit. Okay, in that case, we have the blue lighter 0. Okay, then we have the gray lighter 0. Then we have the blue darker part of a few zeros, right? Then I have the gray darker part as 100. Okay, so this is how it works. You get it? You just need to shuffle these bits a little bit here. So I checked why they want to do that. It's mainly because they want to guarantee that this bit the most significant bit here can represent and also this bit here can represent the sign of this number. Okay. This one, lighter gray. I actually don't know what's going on. Then it is the design is like that. Then we just follow it. Now, I think if we're not a designer, we really don't know what happened in their process. But if they intentionally design something complicated, they must have probably experienced something that we don't know. Okay, this is the B type. Okay, then I intentionally leave out a type, that is the U type and J type. They are relatively easy. Then they also have this type of things, but you understand what that means. So it's basically 20, then grab this part, then grab 11, then grab 10 to 1. Okay, so rearrange the bits. The U type is very easy. Okay, so this is the binary representation for the RV32I instruction set. Then I think it's not really hard to understand many language here, many instructions here. Although there are something that you still need to look at, which is LUI, which is AU, IPC. From the examples, I never used these instructions. Then I want to just briefly mention these things. So fence, this is a relatively later added instruction. It represents the memory ordering. So it kind of sets up the core configuration. So you can execute in this mode and execute in that mode. So for now, we don't really need to worry about this part. And pause and e-break are more related to debugging. Okay, and it's not something that we're useful. But only the e-call here is something I need to mention because we use it in our code. What is e-call? And you probably heard of something called IOCTL call when you are learning operating system. So operating system calls. So what does that mean is basically we write a program in user space, right? Most of the program is executing in user space, and part of your computer is controlled by the operating system. The operating system can perform some options for you. For example, write into a file, then probably something like kill another thread, start a thread, or sometimes allocate a memory page. All those things cannot be done by your user code. Now, only the operating system can take care of it. It's a separation of user mode and privilege mode so that the operating system can keep very stable and keep your whole operating system like safe and not easily corrupted. Like you cannot write a program to detect another program's information and can modify the data of another program. Like in Windows 98, it was 98 it was possible. In Windows XP, it's not possible anymore. So its operating system will take care of these operations. Take care of many of these type of operations. Now, how your user program, how your application can request the service from the operating system is by this eCall or similar instructions in our ISA. So eCall, you can see it's a super simple instruction, right? It's only have an op, that has nothing else, right? Everything else is 0. It's not even encoded. Only it has a certain op. Then so that means when you write the assembly code, it's only eCall, no operand. Now there's a hidden operand that is actually 80, but you don't write it. So 80 is a number, and 80 number is a number that defines which call it is. So your operating system and your hardware need to make the agreement on how this call number maps to the service that your operating system can provide. And even your hardware doesn't really need to care about that. It's all your operating system's definition. Okay, so because since we want to write emulator, but I don't want you to implement a Linux operating system. So I made up 2 eCall numbers. I say eCall 1 is print string. Then eCall 2 is print integer. Then don't take it literally. Read the documentation. I don't exactly remember. Okay. Now eCall 3 is read from stdin. Okay, so something like this. So that you can perform some very basic input and output operations then in your emulator. And you don't really need to implement the whole printf function in your Linux operating system. Okay, question?
So is A0 a register?
A0 is a register.
So
yeah.
you like write to A0 and then the eCall would read from A0 to do the write syscall?
Yes, you first need to write into A0 the number. Then it will perform the write syscall. Then about where to get this number, where to get this string is really by a definition. It's probably just, you can just store it as in A1. Okay, now A1 stores for your number, now A0 stores for this number. Okay. So eCall itself does not have any operand, but it has some implicit operand there. Okay, so your operating system will take care of some operations. So our emulator will perform a very simple operating system that only takes care of these 3 operations. Okay, so last time we also talked about, and we need to come back to the instruction a little bit more to help you start your emulator. So when you start your emulator, a very important task is to lay out a memory. So consider how your CPU runs a process, or how your operating system starts a process. Then it's actually in this way. So we have an address space. We have an address space that is allocated for this program. And we prepare the data in this address space. Then put in the instruction in the right part, and put in the data, the constant in the other important parts. Then we tell the operating system will mark it as this process is ready. It will tell the CPU that this process is ready to be executed. Then today, our computers are designed for multi-thread execution, right? So that means even it's only one core, at one time it can only execute one thread, but if you consider it's run for a very long time, it can easily support many, many threads. How it works is basically by picking up the state from the memory system and start to execute from there. Now, when you want to store the data, when you want to swap to another process, you just simply store the current state into the memory and pick up from another one, right? So starting a process is basically by the same process. You prepare the content of prepare the memory state of the beginning state of your program, then mark it as ready. So eventually your CPU will be able to pick it up. Okay, so we're going to gradually talk about how this memory is organized in different cases so that it can serve as the starting point for your emulator. And so we start with how a function works. Now, when we say a function, it's a small piece of code that there's always a caller and a callee, right? So a caller will call the callee, another function. In that case, this is a function. Then callee always have arguments, return values, and its internal temporary variables, right? So we try to see how these things are organized in the memory. Then I'm pretty much sure you know this concept. Like even you just learned the programming, like C++ or Python programming, you have learned this concept called stack. And when we talk about algorithm, we draw the stack from bottom to up. When we talk about memory organization, we typically organize this stack from top to bottom. So let's say if we're executing a main program, then when we call this function A, then we add a frame for this function called A. Then this frame will store some temporary data that's related to A, right? Then we call another function B, then we grow the stack by adding another frame. Now, when this function returns, we just simply remove this frame. Actually, we don't even need to remove. It's only a pointer that's a pointer pointing to the bottom. Or someone will say it's the bottom of the stack. Someone will say it's the top of the stack. It actually means the same thing. So a pointer is pointing here. So this function returned, we simply point this pointer back to this position, right? To the end of A. So the data, we don't need to override the data. So next time if we allocate, we just write new data there. So rather, you can consider this is a very unsafe method of organizing memory. If you have an array that is allocated in this stack frame and you happen to access some negative part or some positive part, you may be actually modifying some data that belongs to another function, right? That's basically why modern languages like Python and Go eliminated this feature that you can access, like you can do this pointer and calculate the offset relative to a pointer. It's very hard to debug. It's called memory security problem, but it's not really a security problem. It's a debugging difficulty problem. So when we return, we reduce the stack frame. Then when we call another function, we grow. Now we reduce. Now we eventually go back to main, right? This is how we call a function and how memory is organized. So then how Risc-V is handling this is actually you need to know the calling conventions. The calling conventions is co-determined by the program language, by the ISA, and by the hardware that you're using. Okay, so for example, if you're using C, C may have a calling convention. And if you use Go, Go may use another calling convention. These calling conventions may define, say, where we put the argument. Do we put it in a part of a memory, or do we use registers to parse the arguments around? Where do we put the return address, the stack pointer? Is it part of the stack, or is part of the stack, or is part of the memory, or it's in the register file? Now, where to record the caller's context, who to record what type of context, it's all defined by calling conventions. So what is Risc-V's calling convention? At least if you use the Risc-V and you use a standard compiler, it will try to respect this convention. Although if a compiler or a program language is very strong and have a strong opinion, say, we don't want to use this calling convention, we put everything in memory and we don't use register to parse arguments, does that work? And it totally works. There's no problem. But there may be something that is in the implementation that is kind of optimized for this calling convention, so you just don't use this type of optimization. Okay, so by looking at these names, we have some special things. For example, we have this thing called return address, and we have stack pointer. Then we have temporary saved register, frame pointer. Then function arguments and return values and function arguments, right? Saved register temporaries. Those are all related to calling conventions, right? So clearly we can say that it has function argument and return values, right? So that means Risc-V encourage you to use registers to pass arguments, not only using memory. Okay, and there's also a hint that the return values can be more than one, but should not be more than two. Okay. And still, if you want to develop a language that supports more than one program, more than two return values, then you need to break this calling convention and develop your own. Okay, either use memory, or you can just say, oh, I'm fine with using A2 to A7 also as return values. Now, even that, you only have 8 return values. What about user wants to write more? Right. So Risc-V calling conventions are 8, 0 to 7 are function arguments, 0, 1 are return values. We'll talk about the S and the T values later. Now you can see there's a saver. We'll explain what does the saver mean. So let's do a simple function call. This is a simple function call. Now we call a simple function, and there's no arguments and there's no value. What we simply do is to call a JAL, the jump and link. Where we want to jump? We want to jump to this simple label. Okay, so JR. Then when we call, when we execute this line of code, we jump, but with a register, right? What's the register is RA. RA is the return address. That means this JAL is actually doing a hidden operation. This is storing the current PC or the PC of 304. It's storing this PC into the RA register when we're calling JAL. Okay, so that when we return, we know we're returning to 304. Okay, returning to the original point. So although in this function, in this assembly code, RA is not input. It's not an input. It's not a output register. It will write into this register. So this, when you consider hardware design, you need to consider, okay, for JL type of instruction, you need to write, actually need to write 2 registers back, right? Need to write 2 registers back into the register file. What are the 2 registers? One is RA. What's the other one? Huh? No, it's Well, that's something that we also need to consider, but no, it's not the stack pointer, it's the PC. For every instruction, you need to write PC back, right? For regular cases, it will just grow by 4, by 4, by 4. But for jumps, you need to give it a certain number to write back. Okay, so then what about if you have some arguments? Now, when you have some arguments like 2, 3, 4, 5, then you simply, these are move instructions, right? ADDI, and we're basically moving 0 to 2 to A0, 3 to A1, 4 to A2, 5 to A3, and then we do jump and link, right? Now, after we do jump and link, we jump to diff of sums. Now we do some operation. These are all the operations. You can see in this case, our arithmetic intensity is actually very high because we only process data from the register and we don't really need to access memory. This is an advantage of using register as arguments passing. Then you reduce a lot of memory access. So it can be considered as an optimization, but it definitely also limits some sort of flexibility. Okay, then we calculate the result. Then eventually the result is stored in S3, and so this result is stored in S3. Then eventually we put S3 back into A0. Now A0 is the return value. Then we can do jump with register and jump back to RA. Now we know A0 stores the return value. At the end, we put A0 back to S7. Then we continue to use that. I guess your question is why not directly write to A0, right? No? Okay. Okay. That's my question. Okay, you go ahead. What's your?
That question first. Why is it not routed directly to the
What's the other question?
The other question was if there's more than 8 arguments, 8 parameters, does it use like temporary registers or does it push it onto the stack?
It should be go to the stack, go to the memory. Okay. So it's still calling convention. So how you define that, right? You can use S register a little bit. You can use some if you change your calling convention, then or you can just directly go to memory. Okay. So definitely you need to consider some languages that allows multiple returns, unlimited number of return. Then in that case, they have to rewrite the calling convention. Okay, there's nothing forbids you directly write to A0, and it's a better thing. It's just I want to introduce that this is a violation of the calling convention. What is a violation of the calling convention? Because we're saying here, in the caller, we cannot modify S0 to S11. Then, but we can modify the temporary registers. Okay. We can modify the temporary registers. Then you must ask, what if it's calling, like my function is calling another function, and another function, my callee is modifying t's value, right? So how it works is like the next one. But see here, I just want to show you, it violates the rule that we shouldn't modify S3. Okay? By the calling convention. So we need to avoid modification to S3. Definitely we can directly write to 0, but I want to just as a dumb example to show how typically this type of problem is fixed. This is how this problem is fixed. And it's a little bit overkill here. In this case, we consider or caller has some situation, has something, right? Have A0, A1, A3 are used, and S3, we want to use S3, or we also want to use T1, T0, right? So if T1 and T0 are also being used by my caller, I'm modifying data, and I don't want to interrupt the execution of the caller. I don't want to modify the execution of my caller, so it's better. But I still need to use T1, T0, and S3. So what we can do is, at the beginning, we can store it in the stack. So that means we move the SP pointer, we grow by 12 byte, and 12 byte is my stack size. Okay, so the grow is by reducing because it's going downwards, it's going to a smaller address space. Then we move our stack pointer. We move our stack pointer by 12. Then we store SP, SP, SP. You can see why these 4, 8 are used here, why these offsets are used here. We know 0 represents T1, 4 represents T0, 8 represents S3. Okay, it's a stack frame memory layout of putting the different things at different location. Now here in the middle, we didn't change anything. It's still the regular logic of this program. At the end, before we return, we load the data back to the register. So recover the context for my caller. So my caller is not interrupted. Okay, now my caller is not interrupted, and my caller can do whatever. My caller just feels nothing changed. The register state before I call is the register state. After I call is still the same register state, other than A0. Okay, right? Then at the end, before we return, we reduce the stack frame, right? So you see what is actually happening in return is something like this, right? So, or the most important part is these 2 lines of code. So we simply reduce the stack by moving the pointer back by 12 byte. Now we return. Okay, so that also answers the question that SP, the modification of SP is not a side effect of JL, right? The modification of SP is not a side effect of JL because here we need to explicitly modify SP because your core doesn't really know how large your stack frame is. Okay, so question?
Is SP not modified on the subline where it says result equals F plus G?
Which one?
Sub S3, T0, T1.
So T0 minus T1, then we store the result back to S3.
Is that not modifying S3?
It's modifying S3 at this moment, but we recover S3.
Oh, okay.
Right? So we can modify, but then we recover so that caller will feel as if it's not modified. Okay. So then you think this may be overkilling because load and store are not free. They take time. Then any memory access is expensive. We want to reduce them as much as possible. In that case, can we reduce some of the stores, load and stores, so that if the caller is not really using them, then we just let the callee to use it. In this case, the Risc-V make this definition, say, S3, if it starts with an S, is for saved register. That means the callee should not modify it. If the callee needs to modify it, needs to recover it. For T registers, the caller should assume that the callee is modifying it. Okay, so that's why it's called temporary registers. So for those registers, those are changed really fast. And if there are really some useful information there, if there's some really useful information before you make this call, you need to save your T register into S registers. Okay, just if it's in S register, it's safe. If in T register, it will go away. You think it's not important, feel free to override. Now in that case, this is too conservative and the overhead is too high. Now we can reduce it to, in this way, we can reduce the stack to only 4 byte and only stored S3 into the stack, and it's eventually recovering from recover S3 from the stack. Okay. So compared to the previous example, the only difference is we don't store T0 and T1. We only store S3. Then you may also think, oh, this is also why you need to even store S3, right? So definitely you can write in this way, no problem. It's just an overkilling example to show you this relationships. Okay, it's totally okay to write in this way. Okay, just skip S3 at all and only use A2, A1, and A0, and also T registers. Okay, so then immediately I want to write in this format. Then, but I know you probably have this question. Okay, so for non-leaf functions, non-leaf function, it means that this function is called by some other function and is also calling some other functions. In this case, if you are a leaf function, then you don't really need to consider which one is saved. Now for you, everything is saved. If you are not calling any other function, you can use any registers as you want. But if you need to call other functions and you are called by another function, then caller need to save some registers and callee needs to save some other registers. So if you are modifying RA as 11 or even using RA, then you should recover it whenever you are returning. Okay. So the definite rule is written in this table. So what registers are whose responsibility? Who should maintain the state of which register? Okay. So another way to understand the SP, the SP is pointing at the bottom of the stack. Then when you call a function, you grow. Then you grow to the bottom. Then these are some register state you need to save. RA you need to save, as you also need to save, and the local variables, that is, if it's beyond the capability of what the register can handle, you need to save into stack. Okay, then talking about this, then you definitely want to hold as many variables as possible in the register space. But sometimes it's just not enough. In this case, this is called register spilling, that you are spilling the registers. You want to use more registers, but you don't have enough registers. So use your memory to temporarily serve as registers. Then it's definitely not very efficient and add lots of overhead because you need to accessing memory is much slower than accessing register. But that's something you have to do to guarantee correctness. Okay. For CPUs, we don't talk register spilling a lot because the register are not allowed anyway. But for GPUs, register spilling are more common because GPUs, you can consider for each thread there are 256 registers. Then sometimes even that is still not useful, not sufficient. So in that case, we do register spilling by using part of the memory to serve as the register. Okay, so at the end of Risc-V Isa, I want to talk about program memory management. So this part is not strictly related to Risc-V. Pretty much every program that is running in a Unix environment is organized in this way. So the question is, what happens before you start a program? Now, at the beginning, you have high-level code. You write in C++, right, or C. You have a compiler, generate assembly code, and the assembler. Then you generate lots of .o files in that case. Then in that case, you generate lots of .o files. You have object files. And .o files only have the information related to the current file that is being compiled. So if it needs to reference another file, it needs this linking process. So for example, if you are using a function, say I'm calling a function, and this function is only in my header file, but we don't really know the implementation of another. We don't really know the implementation of that function that is to be compiled in another .o file. Eventually, we need a linker to combine them together. So in my program, I simply do, say, I want to just be slightly more explicit here. So we write a program, something like include stdio .h, right? Then eventually in our code, we call printf. something, right? So at the beginning, we first compile a .o file. This .o file will know, okay, printf, I know what's the signature, but I don't know the implementation because I don't have the implementation of stdio, right? So eventually I will leave I will know, okay, here, this is printf. Where to find it, I will leave it later. So I'll leave it as a placeholder that I know printf, but I don't know where it is. It's only a placeholder. At the linking process, so there are two linking processes, static linking and dynamic linking. Static linking means going from .o to exe. Well, Linux doesn't have exe, but just executable file, okay? Then we need to find the reference for printf, then put it in one executable file. It's a static linking process or compile time linking process. Or it can, even in the exe, it can be still a placeholder. If it's still a placeholder, when you execute it, you need to find the dynamic linking libraries. In Linux is .a file, or in Windows is .dll file. Then that at the runtime, we need to fill in this placeholder to get this implementation. Eventually, the linker, no matter is at execution time or at compile time, then we'll find all the necessary libraries, right? We'll find all the necessary code, binary code. Then eventually, the loader will load the program into your memory, set up the initial memory layout, then for your CPU to pick up and to execute the first line of code. So this is the process. And actually, there's another missing process. If we're slightly more specific to C, then in C or C++ compilation, there are three processes. Other than compiling and assembling, there's another process called pre-processing. So pre-processing basically simply detects everything that starts with a pound sign, with a sharp sign. Then we'll reorganize the file. For example, include is simply replace and search and replace, right? Just remove this line and simply take the whole file content and put it there, right? Or some define macros, they're just simply find those macros and replace with the strings. So when you write a C program, then you probably will get errors. Then like you need to know in which step this error happens. For example, this one include string and include IO stream. File arrow stream file is not found. So this is a preprocessor error because it's trying to combine these files, replace these files. Now, if you get this thing like BC undeclared, right? This is definitely a compile error, like compilation error. Then, if you see something like undefined reference is a linking process that oh, we leave a placeholder for printf, but I cannot find it. So that's an undefined reference. This is a linking error. So when you find linking error, don't try to find syntax errors, but try to see if there's something wrong with your compilation configuration, right? Configuration command. So this linking error. Then after this, we assume we have all the code that is necessary, that we find everything. Then we need to place the data in the memory so that your program can start to execute. And this is a typical layout of your program. So there are something that is common. So for example, we have this thing called text. Text, remember last time when we talk about the assembly file, we start with a .text. That means this part is written in the text section, right? Then this is in the text section, then text section is directly placed from this particular address, right? Remember last time we were having this PC as something like 1050C or something, right? So I don't exactly remember the number, but that is a typical PC. So it's starting from this point, then you offset by 50C, this amount, that's your instruction. So your instruction is this part. Okay. Now what is global data? Global data is for global variables, or sometimes it's also store something like strings. That strings is used by your whole program. So some commonly used data is stored in the global data part. Then you have this dynamic area. For dynamic area, you have two parts. One is the stack, one is the heap. So what's the difference between dynamic and stack and heap? So I can give you a few examples, then you tell me if it's allocated on stack or heap. Int A50, stack or heap? Stack, right? Int star A equals new int 50. Is that right syntax? Stack or heap? Heap, right? Then int A star A equals malloc 200. Stack or heap? Heap, right? It's also heap. These are heap, this is stack. So basically, by the time you compile, when you compile a function, if you know the size of this variable, for example, you know there are 200 bytes for this case, then it's in the stack. In this case, this number can be replaced by a variable, right? If it can be replaced by a variable, then it's part of the heap. So when you allocate on a heap, you need to eventually free it. Now, if it's allocated on the stack, it will allocate and disappear with the grow and shrink of the stack frame. And just slightly be careful. When you write a program, this is a func A, okay? Then you write S equals to a struct. Let's say name this struct as data. Okay, then A D equals 1. Then return S. Is this okay? Well, the start will return S. This is okay, right? You're returning a value because the S itself, the whole thing will be part of the stack. In this case, you can see it actually creates a challenge for Risc-V. How you can use one register to represent this thing, right? If this is a whole data structure, it can be actually quite large, right? Question? Okay, that's the next step. That's the next step. Let's start from here. So if you think this one is 200 bytes, for example, that means when you are returning, you are doing a 200 byte memory copy, right? From one stack frame to the callee stack frame to the caller stack frame. When we return S. So say basically C equals A, then it's actually a memory copy from S to C. It's a memory copy from one stack frame to another stack frame. What happens if you do, not this one, ampersand, get the address of S? What's happening? Yeah, so your stack frame, this is your caller, right? Then this is your callee. This is a data that is on a stack, so S is here, right? When you return, your SP goes back to this point, this S is not valid anymore. So returning the value of the pointer of S is not a valid operation in C or C++. Okay, because this part will be eventually overwritten if you call another function. Okay, so another function. So this stack pointer will shrink, then later on will grow. As it grows, it will call another function. It will override with some garbage data. Okay, in C, this is not okay. In Go, this is okay. Why? Go is trying to do something smart. It will detect this pattern, say, oh, you're returning the pointer, then you are going to use this data somewhere else later. In that case, this data is allocated on the heap. Okay, so Go is just trying to be smart on this thing. Then C wants absolute control. If you know it's on stack, it's on stack. Go is a little bit smarter that can automatically allocate it on the heap in this case. Okay, so I sometimes also find it's a problem for me to optimize performance in Go, because if you allocate too many things, it will create garbage collection overhead. Now, in this case, you may feel, oh, this is on the stack, and there's no garbage collection overhead. Then eventually, it's actually very bad. Okay. So those are stack and heap. It's a very important concept for operating system, how to manage memory. But from the perspective of your core, is basically addresses. They're all addresses. The core doesn't really tell what address they are. Just if you want me to load that address, I will just load that address. Store to that address, will store back to that address. There's something that I also didn't say here. Do you find a slight problem that all my PCs start from 100? What if I have another program, another thread? Yeah. All your program should start with this PC. If your operating system defines this is the requirement. Okay. All your programs start from this PC. Then so you have program 1. Since we have like 20 minutes time, and this is the last slide, let's talk about this. So your P1 will have, process 1 will have 0x00010000. This is your first instruction. P2 also use this address. So when we load P2, are we overwriting P1? No, definitely we cannot allow that thing to happen, right? So how it works is this is handled by virtual addressing. So everything can be solved by one layer of indirection, right? So we really want to use this address, but they shouldn't be actually mean the same thing. They're pointing to different things. So then we say these are virtual addresses. Then in most of the system, it's organized in this way. This is P1, so you will have something called PID, process ID. And process ID, let's just say it's process ID 1, and this has process ID 2. Okay? So then in your computer, we have something called a page table. Now, page table can have many entries, but at the beginning, or the most essential part, are these 3 fields: PID, virtual address, and physical address. Those are the most important 3 fields of a page table. So in this case, we write it down as PID 1 virtual address 0x10000 is actually pointing to the physical address of 0x10000. Okay, Then for PID2, this one is still the same thing, and this is 20000. So in the memory, we actually store in this location and this location. But when the program will fill, it's actually at this location. Okay? And that means when for every load and store, right? For every load and store, and also like fetching a instruction, you need to do address translation. Okay, you need to translate, you need to take PID and the virtual address and to find what is the physical address. And you are actually sending physical address, the right physical address into the memory system to get the right data. Okay, so there's an address translation. Then because we have this physical address, then this address translation process allows us a lot of flexibility. For example, we can have a virtual address. Now, what if we have a 4 GB of memory, but one program wants to use 4 GB memory, another program also wants to use 4 GB memory? Can we allow it? Then you probably have heard of like something called swap memory, right? Or what does swap memory mean? Is like register spilling. Is when the memory is not enough, we spill into the hard drive. So what does it mean by spill in the hard drive? We will never spill this type of addresses. Okay, these are instructions are super important. But for somewhere in the heap that we can is maybe we're not using it. So in this case, we may say it's not here. We cannot find it. Whenever we cannot find it, this is something called a page fault. A page fault is a system interruption. Then when this page fault handles, then your operating system will need to maintain another table. They say, oh, this virtual address for this PID is actually in the hard drive at that particular location, right? So then, oh, this page needs to be accessed. Then you will find a victim. For example, this one is the victim. You find this is a victim. We evict this one we first write this one into the hard drive and bring this one back to a location. 0x1000. Okay, bring back this page to the main memory. So write memory is already very slow. Write hard drive is even slower. So that's why if you run out of memory, or probably if you use a Mac or any computer, when you're allocating too much memory, your computer becomes so much slower. But still, it's still working, right? So that is a sign of swapping, right? So sometimes swapping can be managed in a really elegant way that we don't really need to swap a lot because we guarantee that the part of memory we use is still in the memory. But sometimes you suddenly accessing some part that you don't commonly use, now your whole computer will get very laggy, right? And also, when you are dealing with this type of virtual addresses, you are not dealing with every address. You are not dealing with every 4 byte or every byte. You cannot put every byte in this table. That will be too long. So we need to have a unit. So whenever we swap out or swap in, we always guarantee that we swap this unit. And this unit is called a page. Okay, so a page. Then, so the advantage of a smaller page. So this page can be either large or small, right? So the advantage of a smaller page and large page, they both have advantages and disadvantages. Advantage of a large page is once you search, you find one entry, you can get a lot of information. You have big coverage, right? You have big coverage. You know everything within this page. So you can reduce the number of times you do this translation. But the disadvantage is every time you swap out, you swap a lot of data. Then the latency is even longer, right? That's a problem with large page sizes. So for CPUs, The typical page size is 4 kilobyte. Okay, for GPUs, then it can be anything. They can define different things from 16 bytes to 16 bytes all the way to 2 megabytes are possible, right? So GPUs are super care about performance and much unlikely to do swapping. Okay, so about the address translation, later on probably I will talk more, but probably it will be in a more fragmented way. So because we cannot find a lecture to talk address translation as a dedicated lecture. So we're done with Risc-V Isa. Starting from next lecture, we're going to introduce how the core is designed in with sequential logic or combinatorial logic style. Okay, that's all for today's lecture.